Hello, this is Math 2270 coming to you from the College of DuPage for summer 2020, and the title of this lecture is Orthogonal Trajectories. What are they? Well, they're used in mathematics as a curved coordinate system to simplify the representation of some things. You may recall doing such things with Jacobians. Or, in physics and science, engineering, they're used to represent fields, gravitational, electrical, and other kinds of equipotential curves. Also used in meteorology and so on and so forth. Important stuff. So, suppose we start with a family of curves given by this implicit equation where c is a constant. Now, for this given family of curves, we can draw the orthogonal trajectories, and that is another family of curves. This was G, and we're looking for F's that cross each of these given curves at right angles. And here's an example. The orthogonal trajectory of the family of straight lines defined by the equation y equal kx, where k is a parameter, the slope of the line, and notice it goes through 0, 0, is any circle having center at the origin. X squared plus y squared equals r squared, where r is the radius of the circle. Now, as you look at the picture, you can say, yeah, it looks pretty good to me. We're actually going to prove this one. Similarly, the orthogonal trajectories of the family of ellipses, those are the oval-shaped kind of things, end up being the confocal, having their foci on the same axis, of hyperbolas that look like this, and those are 90-degree angles. And you can say it looks good to me. We will not prove this, and although a serious student may go back and actually do this problem as enrichment. Some of you are getting excited to say, oh, I know what I'll do. I'll take the gradients and do the dot product with them. Well, no linear algebra today. This is going to be our practical approach. So here's what we will do in this course. We will start with and construct the differential equation that is associated with our given family of curves, the lowercase g of xy equals c, and we'll be looking at a uppercase g, and this will have derivatives in it equal to 0. So we start with this, and we get a differential equation that represents those curves. But then we're going to replace y prime in this equation with minus 1 over y prime, because the product of this and this is minus 1, meaning they have to be perpendicular. As a result, we had to obtain a different differential equation, and this differential equation is for the orthogonal trajectories. And then we solve that new differential equation to determine the orthogonal trajectories. All right, so here's the problem. Find the orthogonal trajectories of the family of straight lines y equals cx, where c is a parameter. This is the one we talked about at the beginning. Let's see how you do. Let's see how you did. Okay, so we're going to apply the process that we talked about. So we're going to take the derivative, and the derivative of this equation is just y prime equals c. And so now what we have is y equals cx and y prime equals c, so we can eliminate the c. We can just say that c is equal to y over x, solving the first one, and then this becomes y prime equal y over x. So that's the differential equation associated with our family of curves. But now we're going to replace y prime with minus 1 over y prime. So here is y prime. We replace it with minus 1 over y prime. And we simplify things, and this is our differential equation. You can see that this one is separable. And so you solve this differential equation. That's what we do in the next one when we go through these steps. You should verify all these steps. But what we're going to get at the end of the separation of the variables, you see we have the variables separated right here. And so we just integrate, and we will get that y squared over 2 is equal to, and that is going to be x squared over 2 minus x squared over 2 plus c. We move that to the other side, and you see when we multiply all the way through by 2, we have x squared plus y squared, that has to be bigger than or equal to 0, is equal to 2c, and we could replace that with r squared, and it in fact was the circles like we talked about at the beginning of this problem. Now here is a family of hyperbolic curves given by this equation. You want to find the orthogonal trajectories for these curves. You know what to do. So what we have is that y prime is equal to, this was y, so y prime is equal to minus c over x squared. So we have the original equation, we have the differential equation. Here we know that c is equal to x times y, so we substitute in and eliminate the c. This is crucial. So we get, this is our differential equation. Y prime is equal to negative y over x. And you see that is, again, a separable differential equation. So you replace y prime with 1 over y prime with a minus to make them negative. So we put that in, and now we have this differential equation that we're going to solve to find the orthogonal family. We can go through and solve this. You should check, but again, this is a separation of variables. You get this. Now the signs are different now. This is going to be y squared over 2 minus x squared over 2 is equal to c. And we played a little bit fast and loose with this, but you see that that is a hyperbola. So these hyperbola that are not crossing the coordinate axes are shown there. The ones that cross the x-axis are shown there, and they are perpendicular because we found that they were. Now the next example, what we want to do is find the orthogonal trajectories of the family of curves given by the power function. You know what to do, and I will see you in 12 points.